Hello everybody, my name is Eric Brown and I am trying to solve the universe. And what we're going to talk about today is wave-particle duality. And this is not going to be the same kind of wave-particle duality discussion that you've seen in a lot of other videos. What I'm going to talk about, I will share with you kind of the narrative of my dissection of wave-particle duality as I went through my undergraduate career, and kind of some ways that I started to think about this. So let's begin. When we're first introduced to wave-particle duality as new physicists, as we're introduced to these ideas, or as maybe we're not even studying physics, we're just really interested in physics, that it's often, this idea of wave-particle duality is often conveyed as a fundamental property of the universe, where there's this kind of conflict, this core contradiction in the way that the universe chooses to manifest itself to us. And here's how you could set that up. So you could say, well, we have this thing called particles, and particles have certain properties that we've been spending hundreds of years trying to figure out, right? So they're massive, they're small, we believe they have definite volume, they have kinematic behavior, meaning that you could use position, velocity, and acceleration to describe or encode that behavior. They're rigid, meaning that we believe they move as a single object, that all parts of the object move as one. And they occupy space, meaning that you can't take two of them and stick them on top of each other, or you can't take one of them and put it in two different places at the same time, that there's kind of this occupying of space that they do. On the other hand, the universe also manifests itself using waves, right? And that the waves are massless and that their size is irrelevant. Like waves can occupy large regions. Their behavior is determined by wave equations and boundary conditions. They're fluid, meaning that instead of moving as one thing, there's kind of this continuum of motion across the wave. They're overlapping each other, right? So two waves actually can exist on top of each other. Okay, so this is kind of the construction that's generally given to say that, that the universe will exist either as particles or as waves. And when I'm talking about particles here, for this piece of this discussion, I'm going to talk about just what you'd call the classical idea of a particle. So since, like, over the past 100 years, what we mean by particle has actually kind of changed a lot. And later on in the talk, I'm probably going to use the term particle differently, but for this part of the talk, what I mean is the classical version of a particle, which, let's say, is before the year 1905, like what we thought a particle was before the year 1905. And how the development of physics since that time has kind of built up our language. It's kind of a different story, but let's say, well, before 1905, what did we think a particle was? And before 1905, what did we think a wave was? So my approach to this idea when I first heard it was that it felt strange. It felt strange to me that we would describe the universe as being fundamentally contradictory. And so I actually decided to say, well, is there any way to reconcile these behaviors? Is there any way to do this? And my first attempt at that was pretty successful. So you can take like very introductory quantum mechanics. They'll talk about things like wave packets, where waves will, travel as little clumps, and those wave packets actually solve quite a bit of this problem here, right? So you could just say, presuming that you have waves that can travel in little wave packets, that, yeah, the waves, their size is irrelevant, but they can be bounded, right? They're inside of this little spot here, and if you zoomed out enough, it might look like a particle. Their behavior is determined by boundaries, but if you think of approximating a wave packet as something that has a position, and then it would have a velocity and an acceleration, and those things would be approximately well-defined. And yes, it's fluid, but once more, this wave packet can move as a single unit, and you could approximate its motion as moving as one thing. And yes, waves can overlap, but one thing you start to learn in quantum mechanics is that there are certain kinds of quantum waves that obey exclusion principles, where they can't exist on top of each other. So the idea that that waves, or at least quantum waves, can occupy space starts to make a little bit of sense. So in terms of reconciling wave-particle duality, which was kind of the approach that I felt like I needed to take, like just thinking about things in terms of wave packets actually does most of that reconciliation. However, there's a couple problems, and this one at the top here is a problem. So the fact that we think of particles as being massive and waves as not being massive is one problem. In 1905, there was another problem that was introduced, and that was that we started discovering and articulating and defining photons and photon behavior. And what we discovered is that electromagnetic waves would transfer their energy in discrete packets. And the discreteness, or the discreteness of that energy transfer it prompted physicists to say, well, maybe this is a particle-like behavior. And honestly, there was a previous debate hundreds of years earlier about, the particle versus wave nature of light. And so maybe, that having that as part of our history, it prompted us to kind of resurrect that old dichotomy. And we said, okay, well, we have this weird discrete nature of light that maybe means that light can act like a particle. So we have this problem. And one thing, like as I started to progress in my undergraduate physics career, and the story of this video, like as we go through the developments of this video, I'm phrasing it in terms of as I went through my undergraduate physics degree, because that is how I came to the conclusions that I came to. So as I started to progress, I started to make certain conclusions. First conclusion was, what do we mean when we talk about particles? Do we even know what we mean when we talk about particles? Right? Like when we talk about particles, the only even remotely rigorous definition of what a particle is comes from ancient Greece and Democritus, when he gives this logical construction where you take objects and you start to chop them in half, and the two halves have got to have the same property as the original object, and so you can whittle it down into the smallest possible pieces, and that those things must have certain properties. But mostly it's just a colloquial definition, right? Like you could say, well, in the limit, as you get small, we actually don't really have a super strong guarantee that the particle properties that we would think of, like according to Democritus, these particles would just be little pebbles, right? Like we don't actually have a guarantee as you start chopping them that they still act like pebbles, right? That's really what they are. But that's really the only good definition that we've ever had of particles. Waves, meanwhile, we have a very rigorous definition. There are guiding principles to say this is how we can understand waves. There are guiding equations that allow us to describe wave behavior very, very well. So it's kind of like we don't really know what particles are, but we really, really know what waves are. So in my mind, I just started to believe that maybe this wave-particle duality was not a conflict in nature. It was just a conflict in our understanding of nature. And but if that's the case, then we have to resolve these kind of discrepancies here. So the first discrepancy is that particles are massive, waves presumably are massless, and we have this photon behavior that we've stuck in this particle bucket. Okay, so my first real departure from this really common narrative of wave-particle duality was to kind of admit to myself that there was nothing about the definition of waves that required that they were massless, right? When we think of waves, we usually think of mass being associated with the medium that the wave is traveling through, but we actually don't even know much about mass either. Like we know that E equals mc squared, so we know that energy and mass have some equivalence to each other, but that, like, what does that have to do with waves? Waves don't really seem to say one thing or another about that, so it's not fair to say that they're massless. The second thing was that I realized that it's also not fair to say that photon behavior belongs in the particle bucket, right? Like, for one thing, particles are not defined well enough for us to really say, let's put this thing into this bucket. Like, we don't really know what particles are. So by unambiguously saying photon behavior must be a particle, like, we don't even know what particles are. So who knows? But, the reason it got put in that bucket was because it's a discrete behavior, and we know particles are discrete. However, in 1905, when photons were first discovered, the behavior of a photon did not actually match anything according to any known particle that we knew. Right? Like, the idea that you discretely transfer energy, like, there's that discreteness in there, right? But if you think of the way that a single photon behaves, then if you say, well, a single photon has some analogy to a single particle, well, there were no particles that we knew of in 1905 that behaved like a photon. The way a photon behaves is that it either transfers all of its energy or none of its energy, and that it's fully quantized. Like, it's all or none and nothing in the middle. And particles, according to our understanding of them, our classical understanding of particles, they can transfer energy to each other, but that energy transfer is usually continuous, right? Like, you can have a elastic or an inelastic collision, but the amount of energy that's transferred just depends on the configuration of the problem, and that it's actually a continuous amount of energy transferred. So I decided that it's actually not fair to say that photon behavior belongs in this particle bucket, because this actually doesn't behave like any particles that we're aware of. Okay, so this was where my departure from wave-particle duality began. And by the time I was finished with my undergraduate degree, this was where I ended up, right? Like, I actually started to believe that waves did describe mass and massive objects, and that waves do describe photon behavior. And in this talk, I'm not actually going to talk about photon behavior. It's super interesting. I'm probably going to do another video on photon behavior. But so I'm just going to give you a very quick, hand-wavy explanation for why I believe it belongs in this bucket. And it goes like this, that what we know about waves is that, given their boundary conditions, that there are certain allowed modes of propagation. So there are certain waves that are allowed, and there's certain waves that are not allowed, given the boundary conditions, and we can rigorously define what those are. And the idea that there might be some way to set up boundary conditions such that you've disallowed certain energy transfers and that you've quantized those energy transfers is, in the analogy that we have with modes of propagation, the boundary conditions also quantize the allowable frequencies that you can have in those modes of propagation. So that analogy, in my mind, is a pretty good reason to say this is actually more like a wave behavior than it was ever like a particle behavior. Right? Particles did not transfer discrete packets of energy to each other. It was a continuous transfer of energy. And particles don't have this idea of quantized modes of propagation that are determined by boundary conditions, but waves do. And even classical waves, not even quantum waves, classical waves have this idea of, quantized modes of propagation. So that's all I'm going to say about this photon behavior. And I'm going to finish off this talk and try not to talk about this anymore, even though it's just so incredible. I'm resisting. I'll be strong. I'm going to be strong. Okay. So the rest of this talk I'm going to devote to this piece right here, which is the mass. Okay. So here is where you can kind of say we're ending up, is that it's all just waves. Like, let's not talk about this particle wave duality as some type of fundamental nature of the universe. It's not, right? This is not a fundamental. There is not some core conflict in the universe. And whether or not we decide to talk about that in our popular science culture or in our science fiction, it's actually kind of fun. Like, the idea that there's a core conflict in the universe makes the universe feel more human. So sure, we can keep that idea around for the sake of entertainment. But when we're doing serious physics, it's actually possible to say it's all just waves. And one reason why I think it's important to kind of move away from particle wave duality is because I feel like that it promotes a phenomenon that I call quantum mysticism. And I see serious physicists afflicted with this disease of quantum mysticism, where it's like they pay so much attention to the weirdness of quantum mechanics that it's almost like if there was anything that looked simple or not weird, they would pass it over because they would think that that's just not the way the universe works. Whereas, like if we describe the universe correctly, this is the thing that we touch, that we see and smell every single day, right? It should feel familiar to us. It should feel okay, right? I don't think it has to be mystical. It doesn't have to be weird, and it hampers the ability of our species. So let's please just do away with it, right? In our classrooms, we can do away with it. In our movie screens, fine. In our classrooms, let's just do away with it. Okay, so my sense that wave particle duality is something that needs to be done away with was actually shared. At the time when I first was thinking of all these things, I actually felt like that I was the only person in the whole world. And I felt very lonely, and I felt like I had no recourse. There was no one I could talk to say, hey, I actually don't think it works this way. And it kind of disturbs me that everybody's talking about it like it does work this way. So I'm not the only one. I discovered this quote from a very prominent physicist. It says, this double nature of radiation, meaning wave behavior here, and of material corpuscles, which is like particle behavior, has been interpreted by quantum mechanics in an ingenious and amazingly successful fashion. This interpretation appears to me as only a temporary way out, meaning, presuming we can come up with a better idea, we could probably do away with this idea of wave-particle duality. And the person who said this was the person who put photon behavior into the particle bucket, kind of aggravating this. So I'm going to forgive him because he also said this, right? So actually, I say that jokingly. Albert Einstein really is one of my heroes, and but I now know that there's actually quite a group of physicists who don't really seriously think of wave-particle duality as a fundamental core concept of nature. So I no longer feel alone, which is great. And I'm in good company here, right? Albert Einstein and I. Okay, so let's move on. So so the journey that I took to discover that waves are massive, to take mass from being an unexplained wave behavior to an explained wave behavior, starts in Phil Matheson's class. Phil Matheson is one of my professors, and another one of my heroes, right? So in this class, we were discussing electromagnetic waves traveling in a rectangular waveguide. We were discussing an equation called the Waveguide dispersion equation. And that equation looks something like this. And I'm just going to walk through this, right? So omega here is the frequency of the wave that's traveling down. Frequency, it means how much or how fast is it oscillating in time. And then we have this piece right here, which is representative of the wavelength of the wave, which is how much oscillation in space is there. So this is the timey piece, and this is the spacey piece. And then you kind of have this other stuff here, right? And some of the pieces here that come into play, A and B are the dimensions of this rectangle. N and M are integer values. So like I said earlier, the idea that waves can travel in allowed modes of propagation that are quantized, these N and M integers are basically the quantization of the different allowed modes of propagation inside of this pipe. So the frequencies that can exist inside of this pipe are quantized. There's only a certain allowed frequencies. All right, so I'm in this class. I'm learning about this waveguide dispersion equation, and I'm looking at this omega right here, and I'm looking at this k right here. And these things look interesting to me because in their current form, where this omega is squared and this k is squared, I start thinking about in quantum mechanics, where the energy of a photon is given by a formula where omega is multiplied by a constant called Planck's constant, so h bar. So h bar omega is the energy of the photon, and h bar k would be the momentum of the photon. And so I'm looking at this equation saying, well, what happens if I multiply through by an h bar squared? And, well, this is what happens. So you just get a bunch of h bars distributed through this equation. Now this piece I know is the energy of the photon, and this piece right here I know is the momentum of the photon, represented like this. So I now have this equation where I have E squared equals PC squared. C, by the way, is the speed of light. So E squared equals PC squared plus a bunch of stuff here. However, in relativity, this equation is actually pretty important, right? The equation that contains an E squared and a PC squared also contains another element here, which is actually a pretty important element. And that element is mass. So in relativity, if I wasn't in a electromagnetic class, if I was in a relativity class, the equation would have looked like this. And so I concluded that, well, energy and energy, are, what they mean and what the value is the same here. And momentum, like what momentum means and what its value is the same in both of these places. Which means that what this piece right here is, it's equal to this piece. And it means the same thing as this piece here. And so up to this point, I had, I believed, rightly so, like I believed that photons did not have mass. And what I've since learned is that photons in free space that are freely propagating through space do not have mass. But a photon that is trapped does have mass. The mass can be given by equating this dispersion term with this mass term to get this. So again, you have n and m, which are kind of these integer values that represent the different modes of propagation. And so you could actually say n and m might be addressing the different particles of light that are allowed to travel down this pipe. A and B, again, are just the rectangle dimensions. So one thing you can see about this is that you have this h here. H is a very small number. And then you have C here. C is a very big number. So a very small number divided by a very big number means that this mass is probably immeasurably small. Like we probably would never measure it, but we can calculate it. And we can say that, well, we can start to equate mass with something that is wavy, with something that does represent the wave, some kind of wave property. And that's what, like when we think of mass, it has to do with dispersion. All right, so I had another professor, Alex Panin, and Alex Panin, as it turns out, is one of those other physicists in the world that I met along the way who really does believe that wave-particle duality should probably just be done away, and that he believes everything is waves. So if I was hoping to, be brought back into the fold, back into the orthodoxy of physics, Alex did not help. He actually kind of helped thrust me on my rogue path out into my lonesome journey. But he did so with some pretty compelling arguments, and this is one I will share with you now. So imagine you have a box, and this box, it has a photon inside bouncing back and forth, and it's an idealized box, so the photon will bounce back and forth, let's just say forever, right? Or close enough to forever that you can treat it like it was forever. So as this photon is bouncing back and forth, it's imparting momentum to each side of the box as it hits each side of the box. But the amount of momentum it imparts to each side of the box is balanced. So the box might jiggle a little bit, you might get a little jiggle, but it's not going to be moving anywhere. Like there's no overall force. Like the momentum is balanced, so there's no net force on the box. However, Alex says to me, what happens if you push the box? And well, if you push the box begins to accelerate. Now that the box is accelerating, there's a difference in velocity between when the photon was at this edge and when it's at that edge. That difference in velocity is going to induce a relativistic Doppler shift, or a relativistic Doppler reflection off of this side of the box. And for the photon that's traveling into the moving box, it's blue shifted, and blue shifted light has more momentum. For the photon that's traveling into the edge of the box that's moving away from it, it's red shifted, and red shifted light has less momentum. which means that there's now an unbalanced momentum transfer happening on this box, which means that the box is going to have a force on it. The direction of that force is going to be pushing against you, and it's going to be proportional to the amount of acceleration that you give this box. So that is the Isaac Newton definition of inertia, right? Inertia is a force that pushes back when you push on it. So if I push on something with some mass and I give it an acceleration, it pushes back on me with a force that's equal to ma. Right? This is Newton's second law. So this is a manifestation of inertia that is explainable by something that has only, it has the property of waves, but it also has it's a relativistic wave. So there's a relativistic Doppler shift. So, but we also know that mass behaves a certain way in a gravitational field. Mass will get, a force will be induced upon the mass to push it in the direction of the gravitational field. Well, take your box, put it in a gravitational field. The light that is traveling in the direction of gravity is blue shifted due to the gravitational field, and it will impart momentum on this side of the box. Light that is moving away from the gravitational field is red shifted, and it will impart less momentum. So again, you have an imbalance in momentum that will create a force on the box that forces the box to move in the direction of gravity. So you have this concept of a relativistic wave, which is immediately producing the two macroscopically defined ways that we even know what mass is, right? We know that mass pushes against you if you push on it because it has inertia. We know that mass is a force is generated on the mass to push it into the gravitational field. That's the gravitational force. So this is inertial mass. This is gravitational mass. Okay, so at this point, I'm basically fully convinced that mass can be described by waves. In fact, mass can be described better by waves. Like there's now a mechanism in my mind that says, I don't have to just say I can describe how mass behaves, but I can actually now start to talk about what mass is and where it comes from. All right, but I had some problems. So what I wanted to do with this information is I wanted to be able to say, given some wave, given any arbitrary wave, I would like to be able to figure out what its mass is. But so when I would look at quantum mechanical equations that were describing particles that had mass, so I'm going to use the term particle here to be the more modern definition of particle, which just kind of inherited all the wavy stuff. So a particle nowadays is just something that's kind of particle-y and wavy, right? So, but there are equations that describe massive particles that are wave equations, and those equations will introduce mass as an extra term in the equation. And if that extra term isn't added, it's called a homogeneous wave, and homogeneous wave equations are considered massless. However, what I was believing, and I believed it based on the example of this rectangular waveguide, that a wave traveling down this rectangular waveguide, when we did that analysis, we started with the homogeneous wave equation, right? So we started with a wave equation that did not have an extra mass term, and that the mass arose from the boundary conditions, not from the wave equation, from the boundary conditions. And so I said, well, if mass is a wave property, it should arise even from homogeneous waves. And so any wave that has dispersion can be represented as a sum of waves without dispersion. And what that means is that massless waves can add together to create massive waves. So, like if you consider that you would have a wave equation that solves the homogeneous wave equation, and that really does mean that it's massless. Say you had two such solutions, you could add them together to create something that's massive. However, you would presume that the sum of those two waves would also be a solution to the homogeneous wave equation, which claims that it is massless. So that's one way to set up the contradiction in this idea that mass is introduced through source terms. And the idea that I was going for is that mass is introduced through boundary conditions. So the only tool that I had to work with were things like Fourier transforms. Fourier transforms decompose those waves into a bunch of massless waves, and that's not what I wanted. I wanted to say, well, given any wave, how do I describe its mass? And so I needed a new tool. And so I came up with one. This is something that I invented, and as far as I can tell, I haven't actually found anybody else who's done anything like this. So possibly this is something that I've invented for the world. Thank you, world. Okay, here we go. So Fourier analysis requires many samples. So if I want to run Fourier analysis to describe something that's wavy, I do it over a region of the wave, and the answer that comes back is a collection of frequencies that are present within that region. But that's not what I wanted. I wanted to know if you could get a single frequency from just a single point in the wave. So I take my wave, I reduce it down to just one single point, and I can say, is this one single point, is there enough information in this one single point of the wave that I could figure out a frequency? And the answer is actually yes. So to describe this, this sentence here is kind of mathy. Let me try to describe it this way. A Fourier analysis will decompose your function into a whole bunch of complex exponential functions. Complex exponential functions are special because they have a constant frequency. So it says, well, whatever your function is, it's some sum of a whole bunch of these complex exponential functions. And since each of these complex exponential functions just has a constant frequency, it's very well defined. You just figure out what all those frequencies are and add up your sum, and now you have your the Fourier transform, which is actually the distribution of frequency. So what I did is I said, well, I'm calling it an eigenfunction of the derivative here. This is also the complex exponential function. A complex exponential function is a function that has wavy parts, so it has sines and cosines, and it has exponential parts. And those two parts are multiplied together. So you can have something that has kind of an exponential envelope with some waves in it, or something that's just wavy, or something that's just exponential. And what I said is, well, if I zoom in enough to one single point of my function, that I would be able to match a complex exponential to just that one point. And I'd be able to match the value of the function and the value of the derivative, such that if I zoomed in, I wouldn't be able to distinguish between my original function and this special complex exponential function. And since the complex exponential function has a definite frequency, I can say that that frequency is the frequency of my wave at that point. Okay, so here's me visualizing this. So what I have here, the solid red and the solid blue lines are the real and imaginary part of an arbitrary complex function. And we're going to call that arbitrary function our original wave, right? And when I say this is arbitrary, I really just, I picked something out of a hat. And as this green line sweeps through, the dotted red and dotted blue lines are representing a complex exponential function that I'm matching to my original function. And you'll see that like in that region right there, it was wavy, and you could see that that wave had a particular frequency associated with it. And so as we come back through there, I'll maybe pause the video, but on the way back, what I'm going to do is I'm going to point out that as the green line sweeps through this point right here, we get a flip in that blue line, and then we get another flip around right here, flip, and then around right there. We see that we're seeing some of this waviness. And you can say, well, whatever this wave is has some frequency, and that frequency for this dotted function is constant. So the frequency for the dotted function is constant across the whole timeline here. But what I can do is I can take that frequency and associate it with just this point right here for my original function. Okay, so here is the result. So solid blue and solid red are the imaginary and real parts of my original function. The dashed orange line is the frequency determined at each point of my function. the dashed purple line is the exponent. So my function is exponential too, right? So this is the exponent at each of those points. Now you see right here where the exponent goes to 0, that was where the function was looking wavy, right? And on this side, the exponent's positive, and on this side, it's negative. And if you were watching, and maybe you can rewind the video, the function grows this way when the exponent is positive, and then the function grows this way when the exponent is negative. So you'll notice I tried to point out that there was something interesting happening in this region where the dotted blue line was flipping, right? This right here is where the frequency is going negative. And I was super happy when I arbitrarily just picked this solid blue and solid red line. I arbitrarily picked those values. So the fact that I got this little negative piece right here, I feel like it's pretty fortunate because it means that I can talk about this for a second. So in the early 1900s, we were running into problems like this where we said, hey, we're getting negative energies, right? And how do you interpret negative energies? And energy and frequency are proportional to each other. So a negative frequency would be a negative energy. And how do you interpret that? And the final conclusion was that what that is an antiparticle. So that's when we started talking about particles and antiparticles. And when you take a wave function, the standard analysis where you decompose that wave function into frequencies would give you a superposition of particles and antiparticles. So you'd say, I have some of this behavior that's a particle and I have some of it that's an antiparticle, and I somehow add these two things together, and I get the superposition of them. Well, this isn't talking about superpositions at all. What this is saying is that in this region of the wave, like say something were to interact with this wave right here in this region, that interaction would be treated as if it were interacting with an antiparticle. And if it was interacting in this region, it would, and say whatever that interaction was in this region, it would be like interacting with a particle, and that it would be a particle that has this frequency here. And again, I'm using the modern definition of a particle at this point, which is mostly just a wave, right? So this, you don't treat this wave, or using this analysis, you don't decompose the wave into a superposition of particle and antiparticle behavior. You just treat it like a distribution of particle and antiparticle behavior. And that in the distribution, you can identify the regions where you get antiparticle behavior versus particle behavior. Okay, so when I was trying to convince my professors that I was not full of garbage with this whole idea, I used lots of math, and it was very complicated looking, I'm sure, and probably super impressive. I bet it was really impressive. But in the end, the final result, the final practical result of all of this was that equations like this, where we are used to thinking of taking our waves and decomposing them into eigenfunctions, and that those eigenfunctions have certain eigenvalues that are constant values associated with them. If you think of this local frequency analysis as being legit, like maybe you're not sold on it, I don't know. I'm sold on it. I think it's legit. That if it is legit, then you don't have to decompose your functions into eigenfunctions anymore. You can just say that my wave function is just a function, and that the thing right here is also a function, and that function has two meanings at this point. The first meaning is kind of a mathematical meaning, which is this is just whatever the function needs to be, such that when I multiply it by my wave function, I get this stuff over here, which is the derivative of the wave function. So that's the first definition, is that you can think of this function as somehow replicating the behavior of a derivative just through multiplication. And that's maybe a mathy way to think of it. But then there is a more physicsy way to think of it, which is that this function actually represents the distribution of energy. That at each point in space and time, that if you were to say, is there one single energy that I could associate with that point in space and time, this is that function. So now that you're not dealing with eigenfunctions and eigenvalues anymore, say you wanted to solve for this energy distribution. Well, that's very straightforward. It does not require complicated math at this point. It just requires some algebra, right? That you just divide. You divide by this wave function. Once you have this idea in place, it took me a little while. I spent several months just trying to convince myself that this wasn't just garbage, right? Like this idea of saying, well, I don't need to mess around with the eigenfunctions and the eigenvalues. I could just treat this thing like it's a function and move on from there. It took me a while to convince myself that that was okay. I now believe it's perfectly fine. But once you do that, there's a similar equation like this that works for momentum. So you can say, well, I now know, given any arbitrary wave, I now know the energy at each point in space and time. I also know the momentum at each point in space and time. And I can take the equation from special relativity that relates energy, momentum, and mass to figure out what the mass is at each point of space and time. And that equation looks like this. Right? And if you think about it, this was the piece that gives us our energy piece, and this is the piece that gives us our momentum piece. So this equation kind of looks like if you take the more traditional view of how you manipulate an equation like this, you would say, well, maybe I treat all of this stuff as an operator, and then I can take my wave and decompose it into eigenfunctions of this operator, and then find the eigenvalues associated with those eigenfunctions. I'm sure you can do that. That's not what I did, though. What I did was just this. I said, well, I just want to figure out what the mass is at each point in space and time. And for my senior thesis, what I'm presenting to you right now is my senior thesis that I delivered in 2005 when I graduated with my undergraduate in physics. And for my senior thesis paper, in order to validate this formula, what I did is I said, well, let's take a box. Let's take a wave that I can just introduce a wave with some known energy, right? So I'm going to stick a wave in my box. It has an energy that I know, and it's a fixed amount of energy. So I know what the energy is. And then I can figure out what the mass is. Well, I came up with a distribution. I integrated over that distribution, and the final result was that the mass inside of the box, due to this wave, is the energy of the wave divided by c squared, which is what you would expect the mass to be for something that is at rest. Okay, so that in my mind validated we'll just say this is an exercise for the reader. So that's all I'm going to say about that. I'm going to return to this slide just so that I can click and make that kind of gray out right there, because mass, as it turns out, is a very explainable wave behavior. Like I'm convinced that using waves to describe mass gives us a much deeper understanding of what mass even is, right? Like if you're just thinking of mass as some behavior that belongs to particles, but you didn't know where that behavior came from, once you start talking about it in terms of waves, you now know mass comes from the dispersion of the wave. That is where mass comes from. And that wave dispersion, like if you dig a little deeper and you say, well, what is it that causes wave dispersion? Well, that is when you have elements of the wave that are at rest, which is totally consistent with mass, right? And what at rest means for a wave is that it has a standing wave component. So a standing wave would be the wave that's at rest, and any wave that has a standing wave component, that the standing wave component is the piece that generates the mass. That is where mass comes from. And once more, I'm looking at this photon behavior line item, and I'm just like drooling because I just really want to talk about it. But I'm going to leave that for another video for another time. So thanks for making it all the way to the end. If you made it to the end, that means you may have liked my video. So if you liked it, then do the YouTube thing, like my video, subscribe to my channel. If you want to share this with your physics nerd friends, this hashtag here, solving the universe, that's what I'm trying to do. So that's all. So thanks for watching.